It's a great pleasure for me to introduce the next speaker is José N. Gomes from Universidade Federal de São Carlos. And he's going to talk about estimates of eigenvalues of an elliptic differential system in divergence form. Thank you very much, José.
Thank you. Thanks for introducing me. Thanks to my friends for coming here today. My special thanks to the organizers to give me this opportunity to show my work. My English is not very well, but I think I can give this talk in English because it's math and I am in my home. Okay. This is a joint work with Márcio Araújo Filho from Universidade Federal de Rondônia, campus de Paraná, Brazil. In this talk, we'll see some applications of this paper, this very recent paper. More precisely, we will consider a countable family of bounded domains in Gaussian Schmidt-Solton that makes the behaviors of known estimate of the eigenvalues of the Laplacian invariant by first order perturbation of this operator. Moreover, in the setting of convex domains, we will address the Gaussian expand case. Basic notations. Let the Gaussian Solton shrink or expanding depends on sign on lambda. Is Euclidean space with your canonical metric, and with this potential function, it corresponds to the self-similar ridge flow solution of the form. I remember that ridge flow is given by this equation here. In this talk, omega is a bounded domain with a smooth boundary. Let us consider a symmetric positive definite 1 tensor T on Euclidean space and a function eta. So we can define a second order elliptic differential operator L in this eta T divergence form as follows. This one. Okay, here is standard for the divergence operator, and this one is gradient operator. If you need more detail about this operator, I can explain after this talk. Okay. Brief comments. Okay. In the books, says this one, but my reason to work on this paper was that different fields of math work here. That's it. That's enough, of course. For example, in this paper, we use spectral theory, Riemann geometry, and partial differential equation. Good. Cites not only the literature about these subjects, which is already very rich, but also it's not unlikely that operating in divergence form may play a fundamental role in the understanding of countless physical facts. It's worth mentioning here the joint work with Juliana Miranda, from which we know some geometric motivation to work with the operator in this form, but in bound domain in Riemann manifolds. In this paper, we show that L appears of our one tensor on M, and we computed the Bochner type formula for it. An interesting fact is that equation, this equation in this paper, relates the operator L to Shen-Yao operator defined. In particular, if we take T to be the I-state tensor, then this relation is likely to have applications in physics. Now we see this complex system of second order elliptic differential equation. This one. This is the main problem of this topic. Here, non-negative constant, and U is a vector value-add function from omega to Euclidean space, and L is defined by this equation. Okay. Brief preliminaries. In this paper, we use this identification. Here, T is 1 tensor, and here 0,2 tensor. Okay. I need to observe that the divergence theorem remains true in this form. Here, this is this one, and another one, stand for the canonical weight volume form on omega and on boundary of omega. Integration by parts formula is given by this equation. So L is formally self-adjoint operator in this space. The more we obtain this equation 3 for all vector value-add function UN P with events on boundary. That's very important. Okay. First step to study the spectrum of our operator. Now we take L to be this vector value-add function to conclude that our operator is formally self-adjoint operator in the Hilbert space of all vector value-add functions that vent on boundary with inner products induced by equation 2 and 3. It's necessary computation here, okay? It's not immediately. Thus, the eigenvalue problem 1 has a real and discrete spectrum. Okay. more notations. And for u, we define gradient u for this equation and t grad u for this equation. Note that here this vector field is 2 Rn squared, and here also, but here is vector field from omega to Rn, so that we have this definition, this one. And here is the norm on here. Okay. More properties. This is very simple property, but this one is for real functions, but another one is for vector y function u and real function f. Besides, we are using the classical norms, this one and another one. Particular case of problem 1. The first one is eta, when eta is a constant and t is identity. Problem 1 becomes problem 4. Okay? This stands for Laplacian operator on real valued functions. Okay? This operator is known as Laplace operator. In three-dimensional case, it shows up in the elasticity theory, and alpha is determined by the positive constant of Laplace. So the assumption on alpha is justified. The interested reader can consult these two papers for more details about this operator. Some known results. It's worth mentioning here the works below, in which we can find some interest estimate of the eigenvalue of problem 4. In our paper, we can get these results as a consequence of our theories. Okay, especially this one by Shen, Wang, and Xia. In the case of that is not necessarily constant and t. Again, identity. Problem 1 is problem 5. Here. This problem that will be used in your application of rigidity. This is called differential Laplacian operator. Okay. I will use this operator. The differential Laplacian and the background and heat stencil are the most appropriate geometric object to study the smooth measure space, especially in gradient with solids, because gradient with solid is characterized by this equation. When lambda is positive, the gradient with solid is shrink. When lambda is negative, the gradient with solid is expand, and when lambda is 0, the gradient with solid is steady. Our first theorem is the universal quadratic estimate for the eigenvalues of problem 1. It's very technical estimate, and the proof is use PDE, spectral theory, Riemann geometry. Of course, I don't make this proof here. I just use it to obtain our applications. But look this part. In this part, delta and alpha, and epsilon is constant. Okay, and it's necessary that this part be positive. Indeed, this part has been appropriately defined in our computation such that this one is positive. It's this one. Okay? Good. We identify the quadratic estimate in theory 1 as the most appropriate inequality for the application of our results. I am talking about this very technical estimate, but very useful. In particular, the constant C0 has a crucial importance for us. Another theorem is this one. But this theorem is like theorem 1. It's very technical, but it's very useful. Motivations for our applications. We begin this exercise by defining a known class of the functions which is closely related to our applications. Non-constant function f is called transnormal function if it satisfies this equation. And f is called isoparametric function if satisfy this equation. Okay. Of course, like equation 7 implies that the Laurent cells hypersurface of F are parallel hypersurface. And it follows from equation 8 that this hypersurface have constant mean curvature. Isoparametric function appear in the isoparametric hypersurface theorem, has constant principal curvature, systematically developed by Cartan on space forms in this paper. More recently, one considered the problem of extending this theory by Cartan to the general Riemannian manifold and studied some properties of 7 and 8 more closely. This is a very interesting paper. Notice that isoparametric functions exist on large class of space. For example, symmetric space, other than space forms. Currently, new examples of isoparametric functions on Riemannian manifolds have been discovered. For instance, the potential function of a non-compact gradient rate solid with constant scalar curvature is a isoparametric function, since we can assume that eta after a possible rescaling satisfies this equation and this one. The first one is Hamilton relation, and second one is immediately from Ritz-Solton equation. But it's necessary that the Ritz-Solton have constant scalar curvature, okay, and non-compact, because if it is compact and it have constant scalar curvature, F is constant, but isoparametric function must be non-constant. In particular, the potential function of the Gaussian soliton is an isoparametric function. Okay, Dirichlet effect and a brief analysis of the constant. This one. Were the main motivations to consider the isoparametric function. This one. To give some application of our results. The quadratic estimate below is a basic result for our applications. This one. This corollary is immediately from theorem 1. And we have this estimate, the quadratic estimate, where C0 is more particular than theorem 1. Moreover, this part is positive. That's an important property. Okay. The proof is immediately from theorem 1. Because here, problem 5, we can take T to be identity. Then we get epsilon delta equal to 1, T0 is equal, T0 is 0, and T start is equal to, I don't know in English. Okay, hence the result of the corollary follows from theorem 1. Okay. Next corollary is immediately consequence of theorem 2. Okay. Note that the constant C0 is natural since we did not impose any restriction on the function eta. We highlight that this constant has an unexpected geometric interpretation. Indeed, let us consider the warped metric G equal to G0 plus this term on the product omega cross S1, where G0 stands for the canonical metric in the omega, whereas this part is the canonical metric of the unit sphere. So the scalar curvature of G, is given by this function. Hence, by rescaling the previous warped metric, we can obtain C0, all C0, as supreme of the scalar curvature on the warped product. Yes, I am talking about this C0. Okay. This fact is very interesting for us. And we ask the following natural question. Under which conditions the inequalities for the eigenvalues obtained from corollaries 1 and 2 do not depend on the constant C0 for a non-trivial function eta? Come back to corollary 1. We define D0 by this equation, so that by corollary 1 we get another estimate to corollary 1. And note that this part is positive. Now from 11 equation, and by applying the recursion formula by Shen and Yang, we get a corollary 3, this one. From the classical Weil asymptotic formula for the eigenvalues, we know that this estimate is optimal in the sense of order on K, this K here. Applications. Example 1, below is a special case of C0 is equal to 0. To see this, let us consider isoparametric function, this one, where lambda is non-zero real number, k integer with 0 and n, between 0 and n. We can verify these equations, particularly if k is equal to n, this function is the potential function of the Gaussian shrink or expand solid. Depends on sign on lambda. If lambda is positive, we have the potential function of the Gaussian shrink soliton. If lambda is negative, we have the potential function of the Gaussian expand solid. We now take at this potential function into the equation of C0 corollary 1, so that we can obtain this equation to C0. Example 1. Let us consider the family of bounded domains in Gaussian shrink or expand solid given by this one. Okay. This property is very important for us. Okay. Where R is a rational number and BR stands for the open bowl of radius R centered at the origin in region space. So we have this equation. For shrink case, we have C0 equal to 0. And for expand case, C0 is equal to lambda n. Example 2, let us consider the domain omega to be the open bowl in Gaussian shrink or expand soliton. So C0 is equal to lambda n over 2 for both shrink and expand case. Okay. Okay. We are now in the right position to give you the interesting application that we had promised. This one, the countable family of domains given by theorem 1, but in Gaussian shrink solid makes the behavior of known estimate of the eigenvalues of the Laplacian invariant by a first order perturbation of this operator. The proof is let sigma I be the eigenvalue of the drift Laplacian on real valued functions with drift function, the potential function of the shrink soliton on its omega L with Dirichlet boundary condition. We note that the constant C0 is equal to 0 just for the shrink case. Then the eigenvalue estimate of the drifted Laplacian are the same as the Laplacian case. Okay. Remark, note that this corollary can be regarded as rigidity inequalities on the family of bound domains given by theorem 1 in Gauss, just in Gaussian sorting. Now we add the expand case. Here, omega, take omega to be the open bound, but in expand case, let sigma 1 be the first eigenvalue of the drifted Laplacian on real valued functions, with drifting function to be the potential function of the Gaussian expand sorting. So we have this estimate for sigma 1. The proof is very simple. Let sigma 1 and sigma 2 be the first and second eigenvalues of the drifted Laplacian in real valued functions on BR with the judicially boundary condition. If lambda is negative, then both eta and f are concave functions on the closure of the convex bound convex domain. Of course. Thus, we can apply theorem 3 by Ma and Liu in this paper. Okay, this paper is about convexity to obtain this relation. Okay. On the other hand, note that we can use this equation for alpha equal to 0 to get this estimate. So we can combine this one and another one to obtain the required estimate. Good. Thank you.
Thank you very much, José.
I'm sorry for my use.
Or comments? It's okay.
Finish.
Is there a question, comments for this? Can you hear me?
Yes.
Sorry, my connection fell down.
It's not very good.
I'm so sorry. My internet didn't work at the end.
Yeah, so we didn't hear you, in fact. We are hearing you just now.
So sorry, my internet fell down. I was thanking José again and thanking everybody. We hope to see you in person again here in Niterói or all over the world. Thank you very much, everybody, for the participation. I will send the participants the videos as soon as I can, and they will be available on YouTube. Okay?
Okay, thank you, Asun.
Thank you, everybody.
Bye-bye.
Bye-bye.
Thank you.
Thank you, Tam, as well.
Bye.
Bye-bye. Bye-bye, everybody.
Obrigada, Assunta. Obrigada, Detang. Caiu.
Beijo.
Parabéns aí.
Oi,
Nossa,
Guilherme.
bom te ver de novo.
Tchau.
Eli, Renato.
todo mundo.
Quase
Sangue.
Congresso de Liberdade.
Excelente, parabéns aí.
Ah, tem o Detang também.
Tchau, tchau.
Obrigado aí, todo mundo. Obrigado por me aturar aqui com esse inglês arrastado. I'm sorry. I just say I'm sorry.